Hey gang, I wanted to make a quick little video showing how to check the normality of differences when you run two samples when you run a paired samples t-test. Often when we run those, we did that at the end of on example 4 and 5 at the end of lecture 8 last week or so, and we want to be able to check those differences to see if they're normal, because that's one of the qualifications for running the paired samples t-test, is that the differences follow a normal distribution. And so very much like we did in lecture 9, where we checked it for the for the F test for the independent samples t-test, we want to be able to still be able to check the normality of the data set for paired samples t-test as well, because often we have these data sets and they're kind of small, and so we're going to want to be able to run the QQ norm, make a QQ norm plot with a QQ line and also a Shapiro test to check for normality. So let me get the data in here and attach that data set. So OC underscore SBP, and let's take a look at it real quick. So remember, this is the example 4 where we had the women on where they weren't on oral contraceptives, and their blood pressures were measured, and then after being on them for a certain period of time later, their blood pressures were measured again. So we're comparing a before and after shot here to see if their blood pressures had increased or not. We don't really care about the increasing so much, but we want to see if these differences are roughly normal. So what we're doing is each one of these rows here represents a different woman and their blood pressures before they were on oral contraceptives to the aftermath of that as well. So we're looking at those things. And so what we want to do is, let's take a look at those differences. Just look at the numbers. So if I take my SBP, the yes group, and the order here doesn't matter for the normality test. You could do the no group minus the yes group and you'd get similar results. But this is what we're going to want to do. We're going to want to use this statement I'm making right now when we do our QQ line, QQ norm, and Shapiro dot test. We're actually going to use this statement. So let's take a look at those differences. There they are. Those are the numbers that we hope fit a normal distribution, so that we can continue on. So we need to start by checking the QQ norm plot, as we usually do, or we've been starting to become accustomed to, that is. I'm going to plot that in there. And the thing you need to make sure is that in your packages, you either need to have stats loaded over here, and let me erase this real quick, or call for the library stats to turn it on over here. Both of those things will work. You can either check the box. Mine's already turned on, but it won't hurt to run it again, because it'll just keep it turned on. And then I can put my QQ norm plot in here. Notice that I kept that SPB minus the yes minus the no here. That's my first entry, so that's my data, are the differences. So you don't have to find the differences and call them something and then plug it in here. You can plug it all in at one time. And I did some other things in here, like play with the color and the characters, like the PCH, remember, changes the symbol. Instead of you can have dots or different shapes representing your points on this graph. And then I changed the character size to make them a little bigger, and the numbers, and I gave it kind of a long title, and luckily this title actually fits across the top, so you'll see that in just a second. And so we produce this nice looking plot here. It looks like it curves a little bit, but we won't know exactly how far away the points are from the line until we create that QQ line. And so the same settings that I had for the QQ norm, I'm going to have in my QQ line. So notice I still kept the yes group minus the no group. I kept my data x equals true in both ways. If you leave that out, then you want to leave it out in both. But I recommend, again, setting this equal to true, so you have your the data values are represented along the x-axis. I changed my line width to be a little thicker than the normal one, so I get set it to 2. I can set it to anything I want. You don't want it to be too thick, but and then I changed my color there just to have some fun with it. So there we go. The blood pressure difference after versus before are represented here. This point way up here in the top right hand corner probably represents that value of 13 that we see in the differences when we calculated them. I wouldn't call that an outlier necessarily here, but it does kind of veer a little bit away from the line. I don't believe that's an outlier in this case. We could do a box plot real quick to see that, but I don't know that that's necessary here. It looks pretty normal to me. I think most of the points kind of adhere to the line. It's not the most beautiful thing in the world, but I don't dislike it either. I'm thinking that we're going to get a pretty high p-value when we run the Shapiro test. So let's run the Shapiro test to check the normality of those differences as well, to kind of back our assumption up here, or what we think is a fairly approximately normal distribution. And let me just do it this way. So there's my SPB again, yes on OCs minus the no on OCs, and voila, when I do that I get a big old p-value of 0.9473. so we can feel pretty comfortable that the differences here are normal. Okay, so that backs up our assumption from what we see in the graph. Let's do example 5 as well. Example 5 was the drug one that we did in the crossover experiment. It had something to do with pain relievers, being on one pain reliever for a certain amount of time and then switching to the other. And so the score, their pain score on a scale from 1 to 10 was what we recorded. And in that example, we probably should have checked normality before we ran that test. This one's actually a problem in a textbook that I found, and makes me wonder why they didn't check the normality of this data set, because as you'll see, it's kind of questionable. So we're going to attach the drugs data set, and then we're going to run our QQ norm and QQ line stuff. I'm going to show this one to you. I'm going to point something out in the QQ norm portion here after I run it. So let's go ahead and run the QQ norm and QQ line stuff, and notice I did drug B minus drug A in both of these. I kept them the same so that I didn't have a difference there, and again I put my data on the x-axis. Okay, so we get this lovely looking little graph here. It's not the prettiest thing in the world, and as you can see, there's 3 points that they're stacked on top of each other, and there's a reason for that. If I just take drug A or B, in this case because it's the order I did them in, drug B minus drug A. Let's do some space so maybe it'll find it for me. There we go, A. You notice I have 3 negative values of -2 in the differences. So when I find just the straight up differences between those scores, they're -2. That's these 3 points right here. And over here are the 2 values of 1 that we see. Okay. And so I kind of question the normality of this data just because of the way this looks. It's not really what I would call wavy or curving, what I call a hooker. Some people would probably say that this is okay. I'm still questioning it, and I want to back it up by doing the Shapiro test. So I'm going to do the Shapiro test real quick. Shapiro dot test. And we're just going to throw in this drug B minus drug A in there and see what it gives us. Boom. So I'm going to bring that on up a little bit. So it gives me a p-value of 0.06373. That's in that marginal territory. I got asked tonight in the Q&A, and there was only really that one question by Hannah, who asked me why we rejected one of the examples from lecture 8, or not why we rejected, but why we didn't reject some. Yeah, those intervals that we talked about, the p-value having to be between, and whether we have strong evidence when we reject versus very strong, marginal, and no evidence. I want you guys, whenever you do a hypothesis test, to stick to those things for the most part, except for the Shapiro-Wilk test. Shapiro-Wilk test, I think you should always reject if you have a p-value below 0.05, and then it's kind of up to you. That marginal territory between 0.05 and 0.10, it kind of, I want you to feel comfortable going either way here, but justify your answer why you feel okay with it. Maybe you think the plot didn't look that outlandish to you, or that like it curved too badly to you. It didn't have what Dr. Trimboli likes to call a hooker, where it actually curves. And so this one's not really doing that, but those 3 points on here on the end aren't really outliers so much. It's just they're stacked on top of one another. And the same thing on the opposite end. But the other points kind of fit along the line, but it kind of looks like it's almost doing a weird S curve kind of thing, if you will. And so that's why I'm questioning the normality here. Again, this is kind of up to you. I want you to always reject the normality if it's below 0.05, but anything above that, it's kind of your call. We ultimately want this number to be a pretty large p-value, kind of like in the last example where we had 0.9473. That's getting close to 1. I'm pretty comfortable saying that data set's normal. This one I would kind of be questionable about, but other people out there, this is a very subjective, graph interpretation is a very subjective thing. Some people would say this is a normal looking plot, and other people would say it's not. I'd say it's on the borderline. You can get away with going with normality here, but at the same time, I would be questioning it. I question the normality of it to myself, just from the look of the graph and the fact that we got this low p-value, even though it's marginal. Okay, I know that sounds confusing, and it is a little confusing, but I'm kind of giving you permission right now. If it's below 0.05 with the Shapiro-Wilk test, reject normality. If it's marginal, it's up to you. I'm not going to mark you wrong one way or another. I might argue with you and or say that I think that really it's the other way. But you get to make that choice there. But if it's higher than 0.10, you can go with normality all the way. All right. So the marginal territory is up to you. But again, lower than 0.05, reject, not normal. Bigger than 0.10, you can say you're comfortable calling that normal. Okay. That's pretty much it. I don't want to go over too much. I don't want to go over anything else really. There are some other normality tests out there. Shapiro, again, happens to be one of the ones that's probably one of the stronger ones out there. There is a package in R called NOR test. I've got a little information, a small information on how to load that in, or the library you need to call forth. But I have it installed over here, so I will show you real quick. It's only got normality tests in it, and unfortunately, apparently, I loaded it twice. But if you look down here in the help menu, once you click on NOR test, it's got something called the Anderson-Darling test for normality, the Kramer-von Mises or Mrs. Test for normality. There's a version of the Kolmogorov-Smirnov test for normality, the Pearson chi-square test for normality, and then the Shapiro-Francia test for normality. This last one is very similar to the one we just ran. As a matter of fact, let's just run it real quick for the heck of it, man, see what happens. So if I go back to packages and load that, let's come over here and do the I think they call it sf.test. Yep. And we're going to grab that drug A minus drug B. Let's see if we get similar results. We should, because it's supposed to be a more simplified version of the original Shapiro-Wilk test. And that one kind of tells me the p-value is a little bit different. All right, so it really depends on the type of normality test you're running. You may get differing results. This one right here tells me that I'm kind of okay with it being normal in this case. The Anderson-Darling test, which was called the ADE.test, on that one would give me error now that has sample size must be greater than 7. Okay, so apparently there's an assumption with the add test that you have to have more than 7 data values. Let's see what the Kolmogorov-Smirnov one gives us. They call it the Lily dot test, it looks like. Lill. Yep. It runs and gives me a rather big p-value as well. So that one also we wouldn't reject normality with that one. So you can see it kind of varies. And so if you wanted to run one of these other ones, I wouldn't recommend the Kolmogorov-Smirnov, but the Shapiro-Francisca. If you wanted to run that one, rather than to double check to see if it gives you a little bit bigger p-value to go with normality, then you can do that to double check yourself. I really want you to give me this value here and interpret it, but this is another way you can check it. All right. Some of those other tests are for specific things, specific types of data sets. We won't get into all that. But that's all I've got for now, and I just wanted to really show you how to check the normality of your paired data. Okay, so expect to have at least one paired t-test on the project 2, and you'll need to do this same format here. All right, with whatever data set I'm giving you. So take it easy, guys, and talk to you later.